Astronomy, Chapter 8, Section 4, Digging Deeper, Eccentricity, Axial Tilt, Precession, and Inclination, Position, Velocity, and Acceleration. You used mathematics to develop models that demonstrate the orbits of the planets in our solar system around the Sun. Your models also help to explain patterns in the motions of orbiting objects. To fully understand how and why the planets move as they do, you must learn how scientists describe and measure motion. First, an object is in motion when its distance from another object is changing. For example, if you are sitting as you read this book, you would probably say that you are not moving. However, you are on a planet, Earth, that orbits the Sun at about 30 kilometers per second. That means that you are also moving at 30 kilometers per second. This example demonstrates that whether an object is in motion depends on your point of view. If you compare your position to the floor, you are not moving. But if you compare your position to the Sun, you are moving quite rapidly. Don't forget that Earth is also rotating on its axis at 1,670 kilometers per hour at the equator. For this reason, scientists describe an object as being in motion if it changes position relative to a reference point or frame of reference that is assumed to be stationary. The motion of an object can be described further by the distance it travels. For example, a train might travel 150 kilometers, or a horse might travel 3 kilometers. You can calculate the speed of an object if you know the distance traveled and the time elapsed. If a train travels 150 kilometers in 1 hour, then it is traveling at a speed of 150 kilometers per hour. In the previous section, you created a model of an expanding universe. You used an equation, speed equals distance over time, to find the speed that galaxies are to find the speed that galaxies move away from each other as the universe expands. Using this equation, astronomers have determined that the planets travel at different speeds in their orbits around the Sun. The average speeds of the planets are shown in the table to the right. Average orbital speeds, there's your planet, and there's your average speed. So Mercury has an average orbital speed of 48 kilometers per second. Venus has an average orbital speed of 35 kilometers per second. Earth has an average orbital speed of 30 kilometers per second, and so on. So you can locate the planet and then move to the right, and so it's all organized. You just locate the row that your planet is in, and then you go to the second column and you can locate the average orbital speed of that planet. Okay, so that's how you use this table. Okay, did we talk about this? You used an equation, speed equals distance divided by time, to find the speed that galaxies move away from each other as the universe expands. Using this equation, astronomers have determined that the planets travel at different speeds in their orbits around the Sun. The average speed of the planets are shown in the table to the right. Okay, so this shows the average speed of each planet. All right, more can be told about the motion of an object if the direction of motion is also known. Velocity is the speed of an object in a given direction. In physics, velocity is defined as the rate at which an object changes its position and is a vector quantity. Vector quantities are direction sensitive. Speed alone has no direction. It is called a scalar quantity. Airplane pilots must be very aware of the velocity of a plane. Pilots must know both speed and direction of their airplane to avoid collisions with other aircraft. Because the planets orbit the Sun along precise pathways, their velocities are described as orbital velocities. Finally, motion can be described in terms of acceleration. Acceleration is the rate at which velocity changes. When just the speed of an object changes, it is accelerating. For example, when you are running in a straight line and you speed up, you are accelerating. When you stop running, your speed decreases. This is also acceleration. It is negative acceleration. When you are running at a constant speed and you just change direction, you are also accelerating. For example, when running around a curved track at a constant speed, you are accelerating. The planets orbiting the sun are another example of acceleration. Each planet is accelerating because it is continuously changing direction as it moves along its path around the sun. Eccentricity. You used a mathematical model to investigate the shape of the orbits of the planets around the sun. Astronomers have spent many years observing the orbits of the planets and developing mathematical models that explain their patterns and their movement. Using many years of data, the astronomer Johannes Kepler, 1571 to 1630, developed three important laws. These laws describe the orbits of the planets. Kepler's first law states that the orbit of each planet around the sun is an ellipse. The sun is at one focus of the ellipse. Kepler's second law states that as a planet moves around the sun in its orbit, it covers equal areas in equal times. Kepler's third law states that the time a planet takes to complete one orbit is relative to its average distance from the sun. This mathematical relationship is expressed as p squared equals a cubed, where p is a unit of time measured in Earth years, and a is a unit of length measured in astronomical units. Figure 1 shows Kepler's second law states that a line joining a planet and the sun sweeps out equal areas in equal intervals of time. Notice how Kepler's laws meet the definition of a law of science that you read about. Notice how Kepler's laws meet the definition of a law of science that you read about in the previous section. The laws do not explain why these phenomena occur, but they are a way of describing the observations. As you saw in the investigate, the shape of an ellipse can vary. It can range in shape from a circle to a very flattened shape, even a straight line. The more flattened the ellipse is, the greater its eccentricity. The greater its eccentricity. Values of eccentricity range from 0 for a circle to 1 for a straight line. A mathematician would say that the circle and the line are special cases of an ellipse. So ellipses would be numbers between 0 and 1, where 0 is a perfect circle and 1 is a perfectly straight line. Mercury is the planet with the most elliptical orbit. It is the closest planet to the sun. I said Mercury, right? Mercury is the planet with the most elliptical orbit. It is the closest planet to the sun. It has an eccentricity greater than 0.2. The orbit of Mars is also fairly elliptical. It has an eccentricity of 0.09. In comparison, Earth's orbit has an eccentricity of 0.017. So the closer it is to 0, the closer it is to a circular orbit. So out of comparing Mercury with Mars with Earth, Earth would have the least eccentric orbit. It would be more of a circular orbit, but it's still an ellipse because it's still greater than 0. And it's not a line because it's not, it's less than 1. Okay, this is a much, and maybe I should talk about what an ellipse. So elliptical means kind of like, I don't want to say egg-shaped, but elliptical is it's kind of like kind of like an oval. Okay. All right. This is much lower. This is a much lower value than even the ellipse ij that you drew in the investigate. Recall that this ellipse looked much like a circle. Suppose you drew an ellipse with an eccentricity of 0.01. Most people would call it a circle. However, it's eccentric enough to make the distance of Earth from the Sun vary between 153 million kilometers and 147 million kilometers. To make things more complicated, the eccentricity of Earth's orbit changes over time. This is due to complex effects of the weak gravitational pull of the other planets. Over the course of about 100,000 years, Earth's orbit ranges from nearly circular to more elliptical. The eccentricity varies from close to zero to about 0.05. Scientists have found that some objects in the solar system have highly elliptical orbits. Comets are a well-known example. As they move closer to the Sun, the icy mix that makes up a comet's nucleus begins to turn into gas and streams away. The result is a ghostly-looking tail and a fuzzy shroud that you can see in Figure 2. Hold on, let me scroll down. Okay. The result is a ghostly-looking tail and a fuzzy shroud that you can see in Figure 2. It is called a coma, and it forms around the nucleus. When a comet gets far enough away from the Sun, the ices are no longer turned to gas. The icy nucleus continues on its way. Figure 2. The comet's head, or coma, is the fuzzy haze that surrounds the comet's true nucleus. Axial tilt, obliquity. Earth's axis of rotation is now tilted at an angle of 23.5 degrees. This is the angle between the axis of rotation and a line perpendicular to the plane of Earth's orbit around the Sun. This is shown in Figure 3. Let me scroll down a little bit. Okay, we'll get to it. All right. I could zoom out, but I don't want to because I want to be able to I want this to be readable for everybody. Visible, viewable. Axial tilt, obliquity. Earth's axis of rotation is now tilted at an angle of 23.5 degrees. This is the angle between the axis of rotation and a line perpendicular to the plane of Earth's orbit around the Sun. This is shown in Figure 3. The axial tilt varies over a cycle lasting about 41,000 years. The angles of tilt range from 22.1 degrees to 24.5 degrees. The greater the angle of tilt, the greater the difference in solar energy striking Earth's surface in the summer and winter. This results in greater temperature differences between summer and winter. This small change in tilt, combined with other long-term changes in Earth's orbit, is thought to be responsible for Earth's ice ages. The axial tilt is also called obliquity. Precession. The rotation of Earth also has a slight wobble. This is similar to the slow wobble of a spinning top. This wobble is called the axial precession of Earth's axis. It is caused by differences in the gravitational pull of the Moon and Sun on Earth. It takes about 25,725 years for this wobble to complete a cycle. As the axis wobbles, the timing of the seasons changes. Winter occurs when a hemisphere, northern or southern, is tilted away from the Sun. Nowadays, Earth is closest to the Sun during winter, on or about January 5th. In the northern hemisphere, do not let anybody tell you that winter happens because Earth is farthest from the Sun. As you saw in the investigate, Earth's orbit is nearly circular. Also, even when one hemisphere of Earth is tilted toward the Sun, it is not much closer to the Sun than the other hemisphere. The difference between the distances of the two hemispheres from the Sun is not significant. The precession of Earth's axis is one part of the precession cycle. Another part is the precession of Earth's orbit. As Earth moves around the Sun in its elliptical orbit, the major axis of Earth's orbital ellipse is rotating about the Sun. In other words, the orbit itself rotates around the Sun. These two precessions, the axial and orbital precessions, combine to affect how far Earth is from the Sun during the different seasons. This combined effect is called precession of the equinoxes. This change goes through one complete cycle about every 22,000 years. 10,000 years from now, about halfway through the precession cycle, the northern hemisphere's winter will be from June to September. This will occur when the Earth will be farthest away from the Sun. On average, this will make winters there even colder. Figure 3 shows the tilt of Earth's axis and its orbital path about the Sun go through several cycles of change. And lastly, inclination. Look at a model or diagram of the solar system. Notice how the orbits of all the planets appear as if you could put them on a flat surface. In geometry, a flat two-dimensional surface is called a plane. The narrow range in which the planets orbit the Sun is called the orbital plane. What are the orbital planes of asteroids and comets? Both are found mainly in the part of the solar system beyond Earth. Although some asteroids can be found in the inner solar system, many are found between the orbits of Mars and Jupiter. In movies, the asteroid belt is often shown as a densely populated part of space. To pass through this belt, one has to dodge asteroids. This is wrong. The asteroids occupy very little space. Another misconception is that asteroids are the remains of a planet that exploded. As shown in Figure 4, the orbits of asteroids are more eccentric than the orbits of planets. They also often have a slight inclination from the orbital plane. This means that their paths around the Sun are tilted from Earth's orbital plane. You can see this in Figure 4 also. As Earth orbits the Sun, it can cross the orbital paths of objects called Earth-approaching asteroids. There is a great deal of interest in finding Earth-approaching or Earth-crossing asteroids. A collision with an object a few miles across could be devastating because of its very high velocity relative to Earth. Astronomers search the skies for asteroids and map their orbits. In this way, they hope to learn what is coming toward Earth long before it poses a danger to your community. So Figure 4 shows the orbit of the Earth-approaching asteroid 1996 JA1 in relation to Earth. Okay, again, that's the orbit of the Earth-approaching asteroid 1996 JA1 in relation to Earth. Comets are loners that periodically visit the inner solar system. They usually originate in the outer solar system. Comets have very high inclination orbits, as much as 30 degrees from the plane of the solar system. In addition, their orbits are often highly eccentric. Astronomers also search the skies for comets. Once a comet is discovered, its orbit is calculated. The comet is observed as it moves closer to the Sun and changes. A collision of a comet's nucleus with Earth would be serious. However, a collision with a comet's tail is much more likely. A collision with the tail would have little, if any, effect on Earth. That is because the tail consists mainly of glowing gas with very little mass.